Zero-point energy refers to the lowest possible energy state of a quantum system. It's like the energy that it still has even when it's cooled all the way down to nearly absolute zero. Now, in classical physics, you could in principle cool a system until all motion stops. But quantum mechanics forbids this through the Heisenberg uncertainty principle. This is one of the fundamental concepts that we have in quantum mechanics, and it says that there is a limit to the precision with which certain pairs of physical properties can be simultaneously known. Basically, you cannot know with absolute certainty both of the quantities at the same time. And the most important relationships here are energy and time, and then position and momentum. A quantum state has a lifetime, and that lifetime is related to how much energy it has. So like really energetic particles like the Higgs boson, they have like very, very short lifetimes. And if you want to measure its momentum with some certainty, then you can't know exactly where it is. The energy-time uncertainty leads to the conclusion that no quantum system can ever have zero energy, because zero energy leads to implications that it also has zero uncertainty in position and momentum, which violates everything that we know about quantum mechanics. So even in the ground state, there must be some leftover motion, some like irreducible energy. And this is the zero-point energy. The term appears in two related but different concepts that I think a lot of people tend to confuse. Now, first off, there's the zero-point energy of bound systems. So we're talking about like atoms and molecules, mechanical oscillators. So if we look at a simple harmonic oscillator in quantum mechanics, it has a ground state energy of 1/2 h bar omega. Now, h bar is the reduced Planck constant, and then omega is the angular frequency. This value, like this is the energy here that remains even when the oscillator is in its lowest quantum state. So for molecular vibrations, this means that molecules continue vibrating even near absolute zero temperature. And we know that this is true because we can measure it. But the second way that it's talked about is the zero-point energy of quantum fields. Now, in quantum field theory, even empty space, the vacuum, it's not truly empty. Fields exist everywhere. So you've got the photon fields, the electron field, the Higgs field, and so on. Like all the fundamental particles in quantum field theory have an associated field. These are what gives rise to the fundamental particles in the standard model of particle physics, and those fields have quantum fluctuations, even when they're in their lowest energy state. Now, each mode of the field, and when I say mode, what I mean is the allowable energy states or frequencies that the fields can occupy. So each one of these modes contributes a ground state energy. When you add up all possible modes, you get what's called the vacuum energy. We can think of zero-point energy as the unavoidable residual ground state energy in both material systems and fields. The main point that I want to get across here is that zero-point energy and vacuum fluctuations are real concepts, and they have observable, measurable consequences. The effects are genuine physics, they're not just mathematical artifacts. However, and this is the most crucial part of it, having observable consequences doesn't mean that you can then extract net energy. The vacuum is already in its lowest accessible energy state. Just because that state has structure and leads to measurable effects doesn't mean that it can be used as a fuel source. To understand this, we're going to first need to explain what the quantum vacuum actually is. In quantum field theory, the vacuum is defined as the lowest energy state of all of the quantum fields. It's not empty in the classical sense because fields themselves are fundamental. They exist everywhere in space-time. Even when there is no particle present, the fields are still there and they still have quantum properties. The problem we tend to see in the media is how vacuum fluctuations get popularized. The most common description that you'll see is this idea of virtual particle-antiparticle pairs popping in and out of existence. The idea being that they borrow energy from the vacuum very briefly, but then they annihilate before becoming real within the universe, and so there's no violation of thermodynamics. And you've probably heard it explained like this before. It shows up in popular science books, it's in documentaries, some textbooks. I've definitely spoken about it before. But the picture can be framed in a very misleading way. Virtual particles appear in Feynman diagrams, which are visual representations of mathematical terms in quantum field theory calculations. Those diagrams are incredibly useful and they give correct predictions, but the virtual particles in them are not literal objects popping in and out of existence. They're just mathematical intermediate states in a calculation. They don't have well-defined energy or momentum, and they don't travel through space, and they're not borrowing any energy. So when physicists talk about vacuum fluctuations being real, we're not actually talking about particles. Now, since fields can't be perfectly still, they have quantum properties, even in their ground state, and so they still interact with real particles and they affect measurements. What we call fluctuations refers to the quantum uncertainty in field values. So phenomena like the Lamb shift and the Casimir force are real physical effects that arise from how quantum fields behave when they're in their ground state. What we call the vacuum, despite being empty, can interact with matter because it has quantum properties, because it's filled with quantum fields. So what we call vacuum energy is real, and vacuum effects are real, but tapping into them as a power source, that's kind of where the physics and the fiction part ways. The main confusion that seems to appear with these zero-point energy grifts is this leap from the vacuum has energy to, oh, well, then we can use that energy. And understanding why this doesn't work requires understanding what makes energy useful in the first place. So energy can be a hard concept to understand because it's simply defined as the capacity to do work. Work is a process. It's when you apply a force over a distance and this action transfers energy. And the amount of work done on an object is the same as the change in its kinetic energy. So work is whatever process you use to transfer energy. So to get energy, you need to, in physics terms, do work. In order to move energy, you need a gradient, some imbalance that lets you transition from a higher energy state to a lower energy state. You don't get work from a system that is in a uniform state. You get work from energy flowing or transforming between different states. This is fundamental thermodynamics. Let me give you some examples. Heat engines. Heat flows from hot to cold, and you can then extract work from that flow. Hydroelectric power. Water flows from high elevation to low elevation, and you can extract work from that flow. Combustion. Chemical reactions proceed from reactants to products, releasing energy in the process. Electrical power. Electric charge flows from high potential to low potential through a circuit. And pneumatic engines, where compressed gas expands from high pressure to low pressure. In every case, there is a difference, a gradient that drives the process and allows work extraction. The second law of thermodynamics formalizes this, that systems evolve towards equilibrium, towards a maximum entropy, where there is no more useful work that can be extracted. Once a system reaches equilibrium, you can't get any more work out of it. This is why the vacuum has zero-point energy doesn't mean we can use it as an energy source. because there's no process that you can do that will move that energy from the vacuum to another place, because there's no state for the vacuum to move into, like no lower state. Let's use water as an analogy, right? You have a glass of water, and when molecules move around, they have a temperature. If you reduce their temperature, they don't move around as much, so they get colder. So if you remove energy from the water, you can, in theory, use it. But the process of taking the energy from the system, like from your glass of water, makes the water colder, eventually freezing it. Once you have ice, there's no more energy for you to remove. The ice isn't going to transition again so that you can take out energy. But the ice itself still has energy because the molecules still move around. They just move a lot slower. Now, I just want to take a moment for the well, actually crowd here, because yes, we could get into Bose-Einstein condensate, but that is overcomplicating a simple analogy, so let's not go there. Think of the ice as the vacuum. It has energy, but there's no process you can do in your kitchen that will take that energy from the ice, because you would need the ice to change into something with lower energy. But Abby, what about? I know what you're gonna say. Like, I know what, like, come on, yes, there are some well-known cases in experiment and theory where it can appear that energy is coming from the vacuum. But these are all misleading, or they're at least misrepresented online. In each case, energy is being converted, not created from nothing. So let's talk about a few of these: the Casimir effect, Schwinger pairs, and Hawking radiation. I've spoken about the Casimir effect a number of times before because it always comes up when we talk about warp drive. So if you are a regular here, then you should be very familiar with the general idea. Two conducting plates attract each other in a vacuum. As they come together, you can extract work. The process is related to the modes that are allowed between the plates versus what's allowed outside the plates, which leads to pressure pushing them closer together. And this is a sort of a quirk where the energy density then appears to be lower between the plates than the vacuum energy, which leads to claims about like negative energy. And this is why it gets talked about a lot when it comes up in warp drive discussions. But what I want to make clear here is that the energy comes from the system, not the vacuum. What's unique is that these vacuum fluctuations allow for the energy to be moved around. So the vacuum is acting like a medium that moves the energy around, the energy that becomes accessible from the experimental system. It is not being pulled from the vacuum itself. Another important point is that it's a one-way system, right? If you want to repeat this process, you have to reset the plates again, which means you have to pull them apart, which costs energy. And it actually costs you more energy to separate the plates than you get from them coming together. Now, at some point, I think I will do a dedicated video on this, explaining the experiment in more detail. And there was also another one in 2011 called the dynamic Casimir effect that uses superconducting circuits. So don't worry for now about how it all works. The important information is that energy is being moved around, not created. Now, the second and third cases that I mentioned are related to each other, and that's Schwinger pairs and Hawking radiation. Real particles can be created using the vacuum in extreme conditions, so near black holes or in strong electric fields. Let's start with Hawking radiation. Now, the popular explanation involves particle pairs, like electron-positron pairs, and the idea is that they're being created near the event horizon of a black hole. And most people will then say that these are particles popping into existence due to vacuum fluctuations, which kind of sounds like saying that they're just appearing out of nowhere and it's just energy being created. The more accurate version is that these particles are produced when a black hole radiates away its own mass energy. Now, in physics terms, different observers will disagree about what counts as particles near a black hole, and the net result is that energy escapes and the black hole shrinks. The black hole is the power source, not the vacuum. For stellar mass black holes, Hawking radiation would be incredibly weak. Like, the value makes it colder than the cosmic microwave background, which means that they would emit less radiation energy than they actually gain just from the background of space, which is why we have never detected Hawking radiation. Only tiny micro black holes would emit enough energy for us to detect, but we've also never observed any micro black holes. Another effect that involves creating electron-positron pairs using the vacuum is the Schwinger effect. This is related to strong electric fields, so something like a very, very, very high power laser. Above a critical field strength, which is about 1.3 by 10 to the 18 volts per meter, the claim is that the field can pull virtual pairs and make them real. Now, a quick caveat here is that this field strength is about 1,000 times stronger than anything that we can sustain in any lab, so we have never done it. But as another aside though, I was recently involved in an experiment that was published in Nature where we were able to create incredibly high intensity X-rays using a process called coherent harmonic focusing. Now, I'll pop the video link in the description if you want to know more about that, because it brings us closer to being able to reach the Schwinger limit, which is really cool and really exciting. Anyway, what's more important about this idea is that the energy that creates these particle pairs comes from the electric field itself, not the vacuum. The process would convert some of the field's stored energy, so some of the energy from the laser, into particle mass energy. The vacuum acts as a medium, allowing the process to happen, but the energy is still being transferred from one system to another. It's not being created from nothing or being pulled out of the nothingness of the vacuum. In both cases, particles emerge from the vacuum, but the energy comes from an identifiable source, the black hole's mass or the electric field's stored energy. The vacuum participates in the process. It acts as a medium because it has the properties that allows for the transformation because it's filled with quantum fields, but it's not supplying the fuel. So, why do people think otherwise? Why is there this persistent belief that the vacuum contains these enormous amounts of extractable energy? Well, it comes back to a calculation from quantum field theory that is the energy bros go-to proof. But is it true? Whenever I challenge zero-point energy champions online, they will always respond with some form of, but Richard Feynman and John Wheeler calculated that the vacuum energy in a single light bulb is enough to boil off all of the oceans. It appears in countless articles. It's in YouTube videos, consistent across Reddit threads and pop science books, as apparent evidence that the vacuum contains this unimaginably vast extractable energy. The problem is tracing where this claim actually comes from. Now, the clearest mainstream reference that I can find appears in a 2003 Guardian article that states that Wheeler and Feynman calculated that the vacuum energy inside a single light bulb could boil the world's oceans. However, the Guardian article doesn't cite a specific paper or publication where this calculation appears. It's presented as an established fact without any source. And it seems to be almost impossible to trace the claim to its origin. It comes up in Wikipedia entries, in, articles online, pop science books, many a YouTube and TikTok video, but there's no clear primary source that tells us where or when this actually happened, whether it was published, whether it was a specific calculation. It seems to be a summary or maybe a paraphrase of something that they might have said or wrote. It could have been in an interview, maybe even a lecture, but the actual source is completely unclear. So we can't take that as scientific proof or evidence for these claims. But does it mean that it's not real, or that the idea isn't real? Well, we can't actually figure out what it's probably talking about. So what the quote might be referring to is summing up the zero-point energy across all the different ways the electromagnetic field can vibrate. You can think of it like a guitar string. So a guitar string can vibrate at its fundamental frequency or at what are called overtones, which are higher frequencies. An electromagnetic field is similar. It can vibrate in many different patterns and each at a different frequency. Now, each of these vibrational patterns has some ground state energy. And if you add up the ground state energy from every possible vibrational pattern up to some arbitrary high frequency cutoff, the total grows like insanely fast. The bigger the cutoff you choose, the bigger the number. And this is how you can get to enough energy to boil the oceans contained in a light bulb. That's why it's worth being clear what that figure does and doesn't include. The boil the oceans number comes from just one field, the electromagnetic field. But the electromagnetic field is only one of the quantum fields that fill space. There's a field for the electron, for each type of quark, for the Higgs, and so on. When we talk about the predicted value of the vacuum energy, we mean the contribution from all of those fields combined, not just light. And it's worth noting that some of those fields have a negative contribution. So the light bulb quote and then the full vacuum prediction are two different parts of the same idea, one field versus every field. Either way, the reason that the number comes out so insanely large isn't about how many fields you include. It's about how high you push that cutoff, since the energy grows with roughly like the fourth power of it. And since that cutoff frequency is arbitrary, there is no agreed upon reason to stop counting at one frequency instead of another, so you could, in theory, go all the way up to infinity. This is where quantum field theory brings in a tool to handle infinity, and it's something called renormalization. Now, we do not need to get into that. We're not going to get into that. What you need to know is that you can choose different cutoffs, which will make the vacuum energy number different by 60 orders of magnitude. The vacuum energy can basically be set to any value in quantum field theory using renormalization, depending on what regularization scheme you choose as the cutoff. Now, another big factor here is that in quantum field theory, what matters observationally is energy differences, not absolute values. It's not about the number of possible energy states. It's about the difference between two of them. You can shift all of your energy values up or down this scale and the physics stays the same. So this huge calculated number doesn't necessarily mean anything physical. It's just an artifact of how you're counting. But the biggest issue with this enormous number for vacuum energy is one of the most well-known problems in cosmology, the cosmological constant problem, or what's called vacuum catastrophe. Using the method in QFT that we just talked about, we can calculate that the vacuum could have an energy density of around 10 to the power of 113 joules per cubic meter on one end, or about 10 to the power of 56 on the other end. Remember, this depends on how you apply renormalization. But when cosmologists actually measure the energy density of the universe, because we can do that through observations of cosmic expansion, they find something that we call dark energy, with a measured density of only about 10 to the power of -9 joules per cubic meter. Dark energy appears to be an intrinsic property of the vacuum, and dark energy is uniformly distributed throughout the vacuum. This is important because in general relativity, energy curves space-time. It affects how gravity works and how the universe expands. If the vacuum really had all of the energy that the theory predicts, like that really, really high number, whether it's 10 to the 56 or 10 to the 113, it would have curved space-time so dramatically that the universe would have expanded impossibly fast after the Big Bang. Like galaxies, stars, and atoms could never have formed and we wouldn't exist. But we do, I don't know if you noticed. So either the theoretical prediction is wrong, something is suppressing the effect, or our understanding of how vacuum energy works is incomplete. This is one of the biggest unsolved mysteries in physics, but the mystery is about why the prediction doesn't match the actual measurement. It's not about hidden extractable energy. The light bulb quote, or like the idea, it's not evidence that free energy is available. It's an indication that we don't fully understand vacuum energy. It like highlights the gap between what quantum field theory predicts and what the universe actually does. And that gap is a genuine mystery. But guys, come on. The mystery isn't why is the government hiding my zero-point generator? So let's say that we're going to be generous. We're going to assume that the observed vacuum energy density, like the dark energy density, the stuff that's actually out there, we're going to assume, let's say, somehow that could be tapped. How much power could you actually extract? Well, we can do some math. Now, like I said, the actual measured value of vacuum energy is 10 to the minus 9 joules per cubic meter. This is genuinely tiny. A modern day LED light bulb uses about 10 watts. That's 10 joules per second. So if you wanted to power that bulb using the observed vacuum energy / dark energy density, you'd need to extract it from about 10 to the 10 cubic meters of space every single second. That is a cube roughly 2 kilometers on each side. Every second. Continuously. Just to power one singular light bulb. Oh, and sidebar, once you've taken it out from that one region, like it's gone. I was thinking about this and I worked out if you could do this in the space between the Earth and the Moon, you would get enough energy to power that light bulb for 53 hours. Like that's it. That within the space between the planet and the Moon, you get 53 hours worth of a 10-watt light bulb powering. I kind of feel like we're doing better with the energy processes that we currently have. Thanks for watching. If you're new here, I'm Abby, I'm a physicist, and I love to talk about the science of science fiction and some of the big questions in physics. Now, if there are any topics that you want me to do a deep dive on, then please do let me know and I will get researching. And also, you guys, can I just ask, because YouTube has this like new feature where you can hype a video. I think you have to do it in the first week that it's out. I would really appreciate it if you would do that and help me to grow on here, because like I research, write, record, edit all of my videos myself, while also trying to finish writing my thesis for my PhD. So please do subscribe if you haven't, and like if you haven't. And if you liked this video, well, you might like my video on why human teleportation can't work. Or you can check out my deep dive playlist here. Stay nerdy!